Well, good afternoon. Just want to start with a couple of reminders. One, the first lab report is due on the 27th, so this is just in a few days. And you will upload those to LonCappa. You'll only need to upload one per group. And then I've provided some important information about the test kits. This is information from the manufacturers, and it's all on the course blog. You'll note that there is some correspondence between me and technical support. One of the things that I learned was that, and this is interesting, but the API kits, the one for GH and KH, the KH is in fact total hardness. The KH that they call they call carbonate hardness is not carbonate hardness, it is alkalinity. I assumed the word carbonate hardness meant carbonate hardness, but apparently in the aquarium hobbyist community, it does not. It means alkalinity. So you will actually have two different test kits that measure alkalinity. So there's, like I mentioned, there's some important information on the course blog. The link to the course blog is on LonCappa. It was also in a message that I sent out the other day. So check that out, and you really do want to check that out before you finish up your lab and submit your lab report. I did some digging because there was some questions about some of the data that was obtained last week. So after actually going in, repeating tests, and trying to get a better handle on what was happening, I contacted the company, and they actually were very good in responding. You'll see all of their responses. So what I want to do today is we're going to look at Lab 2. Lab 2 is a kinetics lab. So we'll go through what you will need to do in order for that lab write-up, and then how you will analyze it. You will submit Lab 2 as an individual. So there's no group work for Lab 2. So the purpose of this lab is to develop a kinetic rate equation. So we're looking at developing a mathematical model for the decay of aqueous chlorine as a function of temperature, and then use that rate equation to help assess the relative costs of a wastewater treatment process, which will in turn inform the process design. So what you're actually going to produce for this is a 1 to 2 page memo with a significant amount of information in the appendix and the supplemental. And we'll talk about that as we move. So just reviewing a little bit about wastewater treatment. Hopefully you remember some of this from ENE 280. But the raw sewage comes into the plant. It goes through a screening device in order to remove any large material. This includes twigs that got in there from if there's connection with the storm sewer. It may be toys that some child flushed down the toilet, large rags that get flushed down the toilet. And then from there, it goes into a grit chamber, and that's where the finer material, it's kind of the size of coffee grinds. Any sand particles, any coffee grinds, eggshells, they get removed in the grit chamber. This is predominantly inorganic, but there is some organic material. In some cases, there's an equalization basin to both equalize the strength of the wastewater and also the flow. And then into a primary settler, where there's about 60% removal of suspended solids, about 30% removal of the BOD. And then from there into a biological treatment system with secondary settling. And then what we're focused on is the advanced treatment. So we're really focused on is here where often what we have is the addition of chlorine, but at the same time, we don't want to release that chlorine into the receiving body of water. So we have a dechlorination step. So chlorine is added as a disinfectant. It's reactive with both inorganic and organic species, but really in this case, it's added in order to react with the microorganisms that is present in the wastewater. It's typically fast acting, and it's added because it's inexpensive. Now, in order to dechlorinate that wastewater, to protect the ecosystem, there's a number of chemicals that can be added, from sodium dioxide to sodium bisulfite, sodium metasulfite. You'll see later, we will actually do some calculations for the addition of sodium bisulfite. And this just gives you a sense of the reaction. So for instance, if we add SO2, it forms sulfurous acid, and that sulfurous acid reacts with the chlorine that is present in the wastewater and produces sulfuric acid. You can also get reactions with the chloramines, and essentially you again produce sulfuric acid and you produce a chloramine. It's basically NH4 with a chlorine. Okay. So we can form a number of compounds. The major thing that we're using it for is because we do not want to release water that contains chlorine or hypochlorous acid or hypochlorite. These are various forms that occur in water. But we don't want to release that to the natural environment because we don't want to disinfect the stream. So when we're looking at kinetics, we typically model kinetics as either zero, first, or second rates. This is an example of a zero order rate. So you can see that the rate, so the change in concentration with respect to time is a constant. It's not dependent on the concentration. And if we plot the concentration as a function of time, you see that it's a straight line and the slope is the rate constant. If you were to plot it as the natural log or the log of the concentration as a function of time, it's nonlinear. And the same is if you plot it as 1 over A as a function of time. A first order reaction is, we can describe that, and I'll write it as dC dt is equal, I'll write it as decay is equal to minus kC. So the rate of change is a function of the concentration to the first power. And if we integrate this expression from C naught to C and from time 0 to time t, we end up with the equation log of C over C naught is equal to minus kt. So if we plot, in this case, if we plot the log of A or the log of A over A naught, either one will work, versus time, you see that we have a linear plot and the slope is that rate constant. If you plot A versus time, it's nonlinear. If you plot 1 over A versus time, it's nonlinear. For a second order reaction, we can write as dC dt is equal to minus k, in this case, c squared. Again, if we integrate that, we have a function that is related to, in this case, 1 over C minus 1 over C naught versus time. And you can see here, if we plot 1 over A versus time, we have a straight line. If we plot A or ln over A, we have a nonlinear plot. So what you will be doing in this lab is you will be looking at the decay of chlorine under various conditions. You will produce a plot like this. You will determine the rate constant. The method you will use for chlorine measurement is referred to typically as the DPD. Nobody wants to pronounce N-diethyl paraphenyldiamine, so they just call it DPD. And what you'll see is a color change. And this dye here is sort of a pinkish color. So what you will do is you will add the DPD, and the color is related to the concentration. The dye absorbs at around 450 nanometers. If we were in the lab, we would actually measure that absorbance with a spectrophotometer, but because we're doing everything remotely this semester, we'll simply do this with essentially a color wheel, what we call a color wheel or a color chart, and we'll relate that the color of the solution to a calibration chart. Now you'll need to make up 2 solutions. One is a mock wastewater solution. So what I've tried to do is to simulate a wastewater that has a BOD of 20 milligrams per liter. I calculated the BOD of a solution, sugar solution. So if you add 1/4 teaspoon of sugar to 1 liter of water, so for instance, you've got 1/4 teaspoon here, I add that to my water bottle, and this is a 1 liter mark on the water bottle, and I mix that well to make sure that the sugar is dissolved. Now I take 1/4 cup here, and I add that to 1 gallon of cold tap water. If you don't have a gallon jug, you have a half-gallon jug, well, you can use 1/8 cup and add that to a half-gallon jug. If you need help with any of these conversions, just let me know, and we'll kind of work through what you have. If you are living in the residence hall, I have asked Joseph, who's the lab manager, to help with preparing the reagents, since I recognize that being in the res hall, you're not going to have gallon jugs, etc. But I need some lead time so that I can make sure that Joseph is prepared. The dilute bleach solution should be made on the day that you're actually doing the experiment. So what you're going to do is you're going to take the gallon of sugar solution, you're going to add a 1/2 teaspoon of bleach to that gallon. If you only have a 1/2 gallon, well then just add 1/4 teaspoon to a 1/2 gallon. You're going to mix that well. You're going to measure the concentration using your test kit. So we now C naught. The concentration should be approximately 4 milligrams per liter. If it's too concentrated, you can dilute with some cold water. Try not to add too much more because otherwise you're changing the BOD, but you can also calculate that if you know how much water you're adding until your concentration is 4 milligrams per liter. If it's too dilute, you can add a few drops of bleach to increase the concentration. You will need for this 4 clear, well-rinsed glass containers. This can just be a drinking glass. These should be at least 8 ounces because you're going to need multiple samples. You want the gallon container or a 1/2 gallon container. This should be well washed, could be rinsed, washed and rinsed juice or milk container. You'll need a 1/4 teaspoon measuring device, 1/4 teaspoon measuring cup. Unless you adjust the volumes, then you'll need different sizes. You'll need clear plastic, so saran wrap type wrap, aluminum foil, and you'll need the thermometer that you have purchased. So you will need the pH and you need the chlorine test kit. Actually, I said pink, it's actually yellow. pH is kind of a pinkish color. So this is just an image from the Taylor 1004 test kit. So just follow the instructions. It's pretty straightforward. And notice it's only in 0.5, 1, 2, 3, and 4. You're going to have to try and interpolate in here and do the best you can in terms of interpolating the concentrations. That's error that we've got in the data. It's the best we can do given the test kit that we have. And that's just a source of error that you'll need to discuss in your lab write-up. So for the kinetics experiment, you're going to measure the chlorine, the free chlorine level. So follow the instructions for free chlorine. You'll also measure the pH and the temperature of the dilute bleach solution. Pour 8 ounces of the dilute bleach solution into each of the glasses. You're going to cover 2 with saran wrap, 2 with aluminum foil. You're going to record the temperatures inside and outside, so basically your room temperature and in the refrigerator. And then what you'll do is, essentially you'll set it up and then you just have to let the experiment sit, okay? So you will measure the decay in direct sunlight, so it's good to do it on a nice sunny day like today. Again, you're going to do that in the clear glass, so you want that wrapped in saran wrap, or at least covered in saran wrap. In direct sunlight, aluminum foil, so you'll get a temperature, potentially a temperature change, but it's in the dark. You'll do no light, so covered in aluminum foil at room temperature, and as long as the light is off, you can either use aluminum foil or saran wrap in the refrigerator. And then what you're going to do is you're going to measure the chlorine residual at a series of times. These are approximate times. If you were to use 10 minutes and then 25 minutes, 42 minutes, it doesn't matter. Just record the time that you're actually taking your measurements. So it's going to be, you'll have to do is, because obviously you can't do 4 measurements at once. So you'll have to adjust those times accordingly. And then once the residual chlorine level is below detection limits, so where you can no longer detect any residual chlorine, that's where you'll end the experiment. So you may or may not need to go out as far as I've included here. It really depends on how rapidly the chlorine decays. It's going to depend, especially on whether, when you're outside, on weather conditions. I did this during the summer. It was a much warmer day, greater sun intensity because it was the middle of summer. So you'll get different results than what I do. You'll need to record the temperature. You also want to record the outside weather temperature, outside temperature. You also want to record, is it a sunny day, cloudy day, etc., because that affects your rate constant. So you're going to present your data in a tabular form. So these will be whatever times you collect your sample. And then I just made up some data, but here we have some chlorine residuals. And note that if you look at this data, I would have interpolated okay? You're going to have to do the best you can with the data you have, with the system you have. And then you're going to plot the data. So you're going to take one set of data, and I want you to plot it with the 3 different models. So here you can see I've plotted the data as a 0 order plot. So we have 0. I have plotted it as a first order plot, and then I've plotted it as a second order. And I've determined the rate constant, the rate constant and the R squared. You see I've got a rate constant for each, and I've got an R squared. Best model that is the first order decay. So as I mentioned, you'll do this for one set of data, and then for all of the data, you will determine a first order rate constant. So this is just for one set of data. You'll do 0 first and second order plots, and then for all of the data, you will determine a rate constant. And as I write here, the data I made up, so do not expect that you're going to get data like this. Although I would expect that you'd find that the greatest rate of decay would be in the sunlight. And that temperature, as the temperature decreases, you will see a decrease in the rate constant or and the rate of decay. So you're going to plot, as I mentioned, if you plot the data, you'll determine the best fit slope. So you'll determine the slope. If you do this in Excel, Excel will give you a linear regression line, so you will have a slope there. You will determine then the observed rate constant, and then you will also determine the confidence intervals for your rate constants. This, if you watch the statistics videos, I believe it's video 4, but what you will do is you will use the same approach as done for calibration curves. So we go through and I explain how to calculate the confidence interval for the calibration data and the slope of that line. It's exactly the same approach. You have a linear relationship, and you then can determine the confidence interval for the rate constant. So you will have K plus or minus some confidence interval at the 95% confidence interval, and that is what you will report in the table. Okay. Your discussion, you will comment on the differences between the observed rate constants determined in the 4 test conditions, and you'll discuss sources of error and how you could reduce those errors. Your discussion should not be long, perhaps a half a page. Write-up for this lab will not be as long as the first lab. What you will, though, do is you will then determine the cost for a dechlorination contact tank. So this is actually the construction costs for a chlorination tank. We're going to assume that they're equivalent. But note, it is in $1978. So we need to update that cost to 2020. And you can update that cost using this ratio here where we have an construction cost index, and you have the value for 1978 and you have the value for 2020. So from that, you can estimate a current construction cost. So that's your construction cost for the chlorination tank. Notice it's dependent on volume. So I go through in the Word file and go through the example of how you're going to take your rate constants. And from your rate constants, you will determine the volume. You also need to calculate the annual costs, and that is dependent on a capital recovery factor and what I've told you to use. And this is again in the Word file, a 5% interest rate and a 25-year payment. And then I give you the chemical cost for sodium bisulfite, and that is $2.03 per gallon. That is 2020 values, and that's for a 25% solution. So what you are actually going to produce is a memo. You were hired for a project at a wastewater treatment plant. We've got a design flow of 2 MGD, and the plant operators wish to install a basin that would operate as a plug flow reactor, and you're asked to analyze and compare the total costs of a dechlorination reactor. You will only consider the cost of construction and the cost of the sodium bisulfite. And you'll compare natural decay with that resulting from the addition of sodium chloride. So basically you've got 2 different situations. You've got a reactor where you're going to just allow the chlorine to decay naturally at whatever appropriate temperatures. So basically you've got a range of temperatures. You've got to make sure that it has decayed. And then you're going to compare it to if you had a reactor where you added sodium bisulfite. Now, you're going to calculate the time required for 99% degradation of chlorine in a plug flow reactor. So if we have a plug flow reactor, ln of C over C naught is equal to minus K. This is the K you've determined, and what you will determine from here is this T. Okay, so that's what you need, is you need a time. Now, this ln of C over C naught, this is the C at time T. So if we have 99% decay, this is equal to ln of 1 minus 0.99. That equals minus K, as I mentioned, that's the K that you determined, and you will determine T. And this T you will then use here. So you'll multiply that by the flow rate that you're given, and you will determine a volume. Okay. Your dechlorination system has to be effective under all conditions, whether it's sunny, cloudy, winter, summer. So assume an average winter temperature of 5 degrees C, which should be roughly the temperature of your refrigerator. And as I mentioned, you'll use that observed rate constant in these calculations. For the situation where you are adding sodium bisulfate, we're going to assume that we have a continuously stir tank reactor. And you're going to assume that the reaction is essentially instantaneous, but I've told you to use a detention time of 5 minutes. So in that case, okay, T is 5 minutes. And again, you'll have a volume. So the volume will be different for the plug flow reactor and the CSGR. And then what you'll do is you'll calculate the tank volume, as I mentioned. You'll determine the 1978 construction costs, update that to the 2020 costs. You'll determine the CFR and the ECA, And sorry, use a 20-year payback period, use 5%. Okay. Notice that there's no chemical costs. So what you're doing is you're just using these equations. So you'll calculate the capital recovery factor, you'll calculate the equivalent cost, and that is what you will report. For the what I call enhanced decay, so that's with the sodium bisulfite, there you'll need to calculate the annual usage of sodium bisulfite. You need that in kilograms per year. Okay, and we have a dosage of 2 milligrams per liter. Remember that what you're purchasing is 25% solution. So whatever volume, whatever you calculate here, when you're actually purchasing it, you're purchasing 4 times as much because it's a 25% solution. And then you can determine the chemical costs for a range of bisulfite concentrations. You're going to repeat this so that you end up with a spreadsheet, and you'll end up with a plot of the annual project cost versus the sodium bisulfite dose. So that's for your enhanced decay. What you're actually producing is this memo. Your report should be no more than 2 pages. There's going to be a lot of appendix, but the actual memo portion of the report is roughly 2 pages. What you will provide to the superintendent of this treatment plant is the size of the reactors and a cost comparison of the 2 treatment systems. So you're going to take that, you're going to determine the decay rates. You'll use the decay rates in determining the volume. You'll use that information to determine the cost. And that's what you reported, because in a general sense, that's what some decision maker needs. They need to know how much is it going to cost and how much space is it going to require. Back in about 2005 or so, when MSU was first looking at whether they should build a new water treatment plant, the report that was produced was a relatively long report and went through all the preliminary design calculations. But it was actually summarized in that case, it was an executive summary, which essentially was the cost, what the issues were, and how much space would it take. That executive summary was then summarized to about 1.5 page memo, which then went to the Board of Trustees, because that's the most the Board of Trustees was ever going to read. They were never going to dive into what was in this big engineering report. They wanted to know how much it would have cost, how much space would it require, and were there any significant problems or benefits of building a full water treatment plant. Okay? Your appendix has all your calculations, has all the methods, has the results. So basically everything that I talked about goes in the appendix. Calculations go in the appendix. And then you will also have the supplemental materials, which are the same as before. And those supplemental materials will contain all of your raw data, images from your lab notebooks, photos documenting your work, all the raw data, anything that provides supplemental information to demonstrate what you have done. And I went into the lab on, actually it was the 20th, I believe, but it went into the lab on Saturday morning. this past Saturday and collected a number of samples, including one from McDonald, a couple from McDonald Hall, because there was some questions by a student about the results from McDonald that the student was getting, and analyzed those. I actually went in again a couple nights ago, took some more samples, which I brought over to chemistry, and they will do some additional analysis on that for much more accurate result analyses for calcium and magnesium. So we'll have much more accurate hardness results for at least a few of these samples. So that's what you'll need to do for this lab. As I mentioned, the lab, you'll turn in your work individually. So you will each produce your own memo. You'll each gather your own data. For the most part, like I mentioned, you should be able to do much of this in the afternoon, set it up, and you just have to take measurements periodically.